Welcome back to the first session of the HoTT-UF Workshop 2020 with our third talk of the day by Taichi Uemura, who will talk about infinity type theories. Welcome, Taichi.
Thank you very much. Yes, so today I talk about the infinity type theories. This is joint work with Kim Yuen. So what is infinity type theory and why do we consider such a thing? Motivation comes from coherence issues on the semantics of type theory. So one of the ultimate goals of HoTT type theory is to connect type theory with infinity category theory in some nice way. But there are coherence issues, namely equalities in infinity category theory hold only up to homotopy, but some equalities in type theory holds more strictly, like judgmentally equal or even more stronger syntactically equal. So we have to fill this gap in some nice way. One successful approach to this coherence issue is to replace infinity category by some strict model. So for instance, every infinity topos can be presented by a type theoretical model topos given by Sherman. And yeah, there are a lot of work in this way, in this line. This is nice, but today I talk about another way, another approach. So instead of modifying infinity category, I modify type theory to something what we call infinity type theory. Basically, the motivation is that so I think the equalities in type theories are too strict. So infinity type theories is a kind of a type theory in which most of equalities hold only up to homotopy. Okay. So this is a very kind of an infinity version of the. I think this is an infinity version of the Curien's approach to coherence issues. So namely modify type theory by introducing some explicit substitution and some explicit conversions. And then the interpretation of type theory in higher structure will become more straightforward. Okay, so basically there are two things to do in this line. One thing is to show that infinity type theory is somehow equivalent to the ordinary type theory. I guess this will be achieved by some form of conservativity. And the second thing is to show that infinity type theories are connected to infinity category theory in some nice way. And actually, the difficult part is equivalence of type theory and the infinity type theory. And in this talk, I talk about this easier part, and this is very straightforward. And the other part is we have a particular conjecture, but basically left out future work. Okay, so right. So yeah, I think there are a lot of things to talk about, but I have only 20 minutes, so I decided that I only talk about a particular example of an infinity type theory without defining what an infinity type theory in general. So basically, I talk about an infinity analog of dependent type theory with unit types, dependent sum types, and extensional identity types, which are denoted E infinity. But again, because I don't explain what an infinity type theory is in general, so I can't explain what an E infinity is. So in this talk, I mainly describe what is a model of E infinity. And the goal of this talk is to give to show that this infinity type theory, E infinity, is a kind of internal language for finitely complete infinity categories. So this is just an infinity analog of equivalence of dependent type theory with the extensional identity types and finitely complete categories. Okay. So in that sense, this result itself is not so surprising, but keep in mind this infinity is just one example of an infinity type theory, and we can develop a more general theory of infinity type theories. Okay. Right. So this is the contents of my talk. So as I said, I mainly talk about the model of E infinity, and the notion of a model of a type theory I have in mind is a natural model introduced by Stivaldi. So I mainly talk about the infinity analog of natural models, which I call infinity natural models. And the theory of infinity natural models will be almost the same as the ordinary natural models, except that the notion of univariance makes sense for infinity natural models. I think this univariance is the only difference of from the ordinary natural models. Okay. So let's start by defining what an infinity natural model is. So it consists of an infinity category C with a terminal object and a map of precisions D from E to U, which is a map of precisions of C, which is required to be representable in the sense that kind of every fiber of some representable precision is again representable. So given map A of this form, then we obtain an object in the category C, brace A, and put back in this form. So this is just essentially the same as the ordinary natural model, except that base category is now an infinity category, and the precisions are now space-valued precisions. Okay, and so the intuition, so a natural model is sort of as a model of a type theory. Precisely, it models basic structural rules of dependent type theory. So basically, the objects in the category, base category C is a kind of a context, and sections of U is a kind of types, and this object brace A is a kind of context comprehension, which is in a context obtained from gamma by extending X colon A. Okay, so so infinity natural model is kind of will be a model. So infinity natural model will model some basic structural rules of infinity type theory, whatever it is. Okay, so let's consider type constructors like unit types, sigma types, and identity types. In general, type constructors on a natural model, infinity natural model is modeled by maps between precisions. For instance, the unit types, the unit type is modeled by a pullback square in this form. So this map 1 is corresponds to the type constructor, and the T corresponds to the term constructor. And being a pullback means that T is the only element of the unit type. In this way, unit type is modeled by a pullback square in this form. Okay, and similarly, sigma type is also modeled by a pullback. It looks like this. You don't have to care about what the composition of polynomials. Here, I only emphasize that sigma type is also modeled by a pullback. Okay, so the meaning is sigma is again a type constructor, and P is a pairing constructor, and being a pullback means that the pairs are the only elements of the sigma type. Okay, then and the identity type is also modeled by pullback. Again, ID is the type constructor, and R is a constructor of reflexivity. And being a pullback means that the reflexivities are the only elements of identity types. So in that sense, this identity type is a version of extensional identity types. And in the ordinary type theory, extensional identity types destroy higher dimensional structures. But here, but for infinity type theories, extensionality of an identity type means that elements of identity type like this are equivalent to kind of homotopes between A1 and A2. So it doesn't collapse higher dimensional structures. Okay. Right. Okay, so the definition of an infinite natural model and type constructors on them are really the same as the ordinary natural models. And what makes infinite natural model interesting is the notion of univariance. So the definition is very simple, because an infinite natural model is just a map of precisions of some infinity category C. So the being univariance makes sense in the infinity topos of precisions over C. Okay. So a nice thing of univariant infinity natural model is that type constructors like unit type, sigma type, and unit types become now properties rather than structures, in the sense that if these are univariant representable map, these are univariant. If these are univariant infinite natural model, then the unit sigma and identity type structures are unique. I mean, unique up to contractive choice. And these structures exist if and only if the class of pullbacks of D has certain closure properties. For instance, D has sigma type structures if and only if pullbacks of D are closed under composition, for instance. And this is basically, this is mainly just the definition of a univariant map in the infinity topos. Okay. So finally, I'll explain about democratic infinity natural model. It is just an infinity natural model. It is a kind of infinity natural model which will be syntactically generated. Precisely, an infinity natural model is democratic if every object in the base category C is looks like context. In other words, every object is reachable from the terminal object by finitely many context comprehension. Okay. So yeah, okay, I have defined all important concepts, I guess. Okay. So I give an example of infinity natural model. So let's see be an infinity category with finite limits. Then we can form a map of precipes DC from EC to UC, like UC of X is the space of objects of slices, and EC of X is the space of pointed objects of slice, and DC is just a forgetful map. Then this map DC is representable. It is not so difficult. But moreover, this map DC is the universal representable map, or generic representable map, or representable map classifier, in a sense that any representable map of precipes over C is a pullback of this particular representable map DC. And such a pullback must be unique up to contractive choice. So with this property, this DC is automatically univariant, and I think it is. And this infinite natural model is democratic. I think it's almost by definition, and it has unit types and sigma types. So for sigma type, it has basically DC has sigma types because representative maps are closed under composition. So straightforward. And it also has an identity type structures which come from finite limits in C. Okay. All right. So now I can state the main theorem in this talk, which asserts that these universal representative maps are the only examples of democratic invariant infinite natural models with these type structures. So to make it precise, I call such a model. I define a model of infinity to be a univariant infinite natural model with unit sigma and identity type structures. And we write like this for the infinity category of democratic models of infinity. And then we have the obvious forgetful factor from democratic models of infinity to infinity categories. And the theorem is that this forgetful factor factors through the subcategory of finitely complete infinity categories and left exact factors. And induces the equivalence of like this. So it is precisely so. In other words, E infinity, this infinity type 3 E infinity is kind of internal language for left exact infinity categories. And a quick proof is that inverse is just given by the universal representable map. Okay. We have further results and conjectures. So first of all, we'd like to give some connection between infinity type theory and type theories, as I said. And for this particular infinity type theory, E infinity, we have some conjecture. So first of all, well, recall that Kaplan and Ramstein constructed the left-side model category of contextual categories with unit sigma and intentional identity types. And so which means that by formally inverting weak equivalencies, we get infinity category of such contextual categories. And we can construct an adjunction between democratic models of infinity and the localization of this left-same model category. And we conjecture that this equivalent, this adjunction is an equivalence. But, and also, we can develop a general theory of infinity type theories. And for instance, for each infinity type theory, we have some infinity categories, like infinity category of models of T, or theories of T, or democratic models of T, and so on. And have a nice theory of infinity type theories. And we have some more interesting infinity type theories, like infinity type theory with pi types, whose democratic models are equivalent to locally Cartesian closed infinity categories. So this infinity type theories are internal language for locally Cartesian closed infinity categories. And another interesting infinity type theory is infinity type theory whose democratic models are equivalent to infinity type theories. It sounds a little circular, but it makes sense. And we can also consider some inductive types, like empty types and pushouts, which will correspond to stable, Purback stable finite colimits. But it's not clear how to define more general higher inductive types. And also, it would be nice if we have some syntax for describing infinity type theories. Yeah. Actually, I call them infinity type theories, but we don't have any syntax for infinity type theories, so maybe it doesn't look like type theory. So it will be nice if we get some nice syntax, but it's future work. Okay, this is the end of my talks. Thank you very much.
Thank you very much, Taichi. Are there any questions for Taichi? Yeah, Shaitanya, go ahead.
Hi. Just a quick question. The identity type structure on the model given by a finite limit category is probably just the diagonals, right? You said there's a unique identity type structure. There you go.
Well,
Yeah.
This.
Right.
Sorry, that's diagonal. Yeah.
So,
right. Yes.
Yeah, that's what it is, right?
Right.
Okay, that was just like a sanity check. Thanks.
Are there any more questions? Okay, I have a question. You mentioned that in a univalent model, sigma types, I think, are unique, and maybe identity types as well, if they exist, so they are property rather than structure.
Yeah, right.
Is this the case also for the representation, when we talk about representable maps versus represented maps? So it looked like you call them representable, but they actually equipped with a representation. Meaning with this pullback structure, if it was at the very beginning, you mentioned that. Yeah, here, exactly. Is that structure also
no, it is
unique also, in some sense, if it exists?
Yeah, it's also unique because it's just, because it's a representation. So,
well, it's essentially unique, or is it?
It's a unique up to characters, and I regard it as a property of this map.
Okay, thank you. Are there any other questions? No, if there are no more questions, then let's thank Taichi again. And we will have a break, a coffee break of about a bit more than half an hour now, and we will resume here